So here we are going to go over the homework titled Group Activity. So this homework asked us to look at different sets of elements paired with operations and determine if it was a group. Remember, a group means that it has an identity, everything has an inverse, and that it's associative. Associative property is a little bit hard to prove, but most of these examples actually do the opposite in those scenarios when they're not groups and prove that something is not associative with a counterexample. However, if it is a group, I also want you to say if it's a commutative group. If it wasn't a group, we're just supposed to say why. So if we take a look at question number 1, this is one of those ones I was just mentioning where it's a little bit difficult to tell at first. However, it is not going to be a group. So the answer for this one ends up being no. And that would be because we can provide a counterexample of why it is not associative. So if we want to prove that it is not associative, we can use a counterexample of that. You might have found a different counterexample than me. As long as you go through the same steps I'm about to show, that is absolutely fine. But here's my counterexample that I wanted to use for this at operation with these elements R, S, T, and U. If I try to do R at parentheses U at S, I will actually be able to show that that is not equivalent to parentheses R at U, close parentheses, and then follow up with an at S afterwards. So in this situation, U at S in parentheses, as we can see from the chart, ends up being T. So that would be R at T left behind. And then R at T, we see from the chart, is R. That ends up not being equal to a different grouping since the parentheses are rearranged here. R at U, if we look at the chart, is T, and T at S ends up being S. And so, no, this is not a group because it is not associative. In the next chart, where we are pairing S, T, A, and R with the question mark operation, this once again was a no, as many problems on this homework ended up being. And this is not going to be a group because of one major key. If we want to look, we can see that there is star in both the R row and column, so it seems like it has an identity of R. But when I go and try to look at the A row specifically, I can't find an inverse for A. So since we can't do that, it appears that A has no valid inverse. It does if you look down, however, it doesn't when it's across, and that wouldn't make any sense for it not to work one way but work for the other if it did truly have an inverse. So A has no valid inverse in this case. Right, we're going to look at the problems on the back. As I said, many of these end up being no's. All right, however, unlike some of the other ones so far, numbers 3, 4, and 5, they end up being just literal operations that we've dealt with, like multiplication, addition, and subtraction, along with different number sets that you should be a little bit familiar with. Whole numbers, integers, and then a little bit more of a unique group that maybe you don't know the name of, but this is the powers of 3, which we're going to talk about a little bit more about powers throughout this whole school year. So question number 3 also once again was a no. And that's because if I'm thinking of how inverses work with multiplication, they would be two elements multiplying together to become the number 1, multiplication's identity. And so a counterexample of why this does not work is 3's inverse in this situation would be 1/3. However, the number 1/3 does not exist in this set. So there is no existing inverse. Okay, so no inverse for 3 would be an example. It also works for every single other number in this set with the exception of 1. 1's own inverse is 1, but anything else, it didn't have an inverse. And that ended up being true for question number 4 as well. Addition and the whole numbers, well, that pairing's not going to end up having an inverse. The whole numbers are going to be 0, 1, 2, 3, 4, continuing in that pattern infinitely. And so if I try to figure out what the additive inverse of something like 2 is, okay, it's going to show us that no, this is not going to be a group because 2's inverse in this situation should end up being -2, but -2 is not a whole number. Okay, so a counterexample would be no inverse for 2. Just like before, there is the identity present in this set, being 0. However, unfortunately, if any of them don't have an inverse, well, then it's not going to be a group. And then we move on to our last and final no, it is not a group, and it's going to become, once again, that it's not associative. Okay, so we're going to answer that right away, and I'll show you my counter example of that. So the associative property does not hold. One example for the integers in subtraction would be something as simple as 1 minus 2 in parentheses minus 3, not equaling 1 minus the 2 minus 3 in parentheses instead. And that would be because 1 minus 2 is -1, -1 minus 3 is -4, but over here we have the 2 minus 3 that we would complete first and get -1, and 1 minus -1 is 2. So these do not equal each other. Now, number 6 was a challenge question because I did tell you that proving the associative property is not something we can do outright for every situation. However, that cycling or cyclical pattern that I've mentioned in the past is present here, which means this does end up being associative. If you don't remember what that cycling pattern is, if we look at the original elements, pesto, which we find here in row T, okay, pesto is present. The P, as we move down, wraps around to the end, and E, S, T, and O all shifted over 1. Then the E would be placed at the end, which we have to go back up to the top of this chart to see, and then the STOP, stop, moves. Then the S moves to the back, and the TOPE moves forward. The T moves to the back, the OPES moves forward, then the O making the PEST back to pesto, and that cycling keeps continuing. So this one ended up being a yes. And in the long, big scheme of things, that means now I can finally answer those questions I put on the front of the page, which, if you remember, they were, if it is a group, say the identity, say the inverses for everything, and say if it's commutative. And so if we go back to that last example problem, we end up having pesto appearing at T. So the identity for this ends up being T. We can then try to find our inverses now that we know the identity. And so P has to pair with something to make T as an answer. P with E makes T. So does E with P. So they are each other's inverses. An identity is always its own inverse, and we can see that in the chart that a T and a T produce the identity still. By process of elimination, that means our last pair of inverses must be S and O, and sure enough, S with O makes the identity, O with S makes the identity. So they are each other's inverses. And then lastly, we can show that this is commutative if we draw our diagonal line of symmetry along the operation diagonal, and we can see that we have some symmetry going on here. For example, on either side of the line of symmetry, we have those two T's. Here we have these two O's. Then we have a double P repeating on either side for this diagonal line of symmetry. And then that pattern does keep going throughout the rest of the chart as well. So this brings us to the end of this homework review. If you need to, what you can do is you can go back and look at any of the examples again by scrubbing through the video. Otherwise, you can go ahead and take a look at the answers to the review sheet for tomorrow's quiz.